Okay. Okay, I'll start recording. So again, my name is Tang. I'm a applied research scientist from NVIDIA, and I will host today's talk. Let me introduce today's speaker, Dr. Youbao Tang. He's a senior research scientist at PAII Inc., where he works on doing research and making products on using deep learning for medical imaging and clinical informatics, such as universal lesion analysis in CT images and intelligent PACS, and developing algorithms of using deep learning for video-based tasks, such as human detection, tracking, pose estimation, and action recognition. Prior to this current position, Youbao conducted a 3-year postdoc fellowship at NIH, where he focused on large-scale medical imaging analysis using deep learning. He received his bachelor's, master's, and doctorate degree at the Harbin Institute of Technology in China, where his research interests include computer vision and pattern recognition. His research has been recognized by awarding 2 RSNA training research prizes as the first and the second author, respectively, and the NIH Fellows Award of Research Excellence. Youbao.
Thanks for your introduction. Can you see my screen?
Yes, I can.
Okay. Yeah, today I'm very glad to have this opportunity to talk to you about automatic RECIST emitter prediction and the lesion segmentation. The title of this talk is accurately measuring the tumor size on CT scans with minimal human efforts. So this talk will cover a series of deep learning-based methods published recently for this topic. And this is the outline of this talk, including 6 parts: the background, box-based RECIST emitter prediction and lesion segmentation, click-based RECIST emitter prediction and lesion segmentation. Then I will give some demos to show the applications our methods can be used for. Lastly, several simple points will be summarized. So let's get started. So in radiologists' routine work, they have to compile the CT scans collected at different time points to find the abnormal regions, do the follow-up studies, and annotate the RECIST emitter to measure the lesion size using the PACS. The whole process is heavily time-consuming and tedious. Therefore, how to automate these steps is a clinically important problem, which is very useful. In the last 3 years, our team focused on solving this problem by developing different tools for different tasks, such as point matching, is used purpose to do the comparison by radiologist, and the lesion tracking. We try to develop some track method to find the lesion at different time points. So this we can consider this as to try to help doctor to do their follow-up study. And also we try to propose some method to do the auto measurements. So we can use some tools to predict the RECIST emitter and also do the lesion segmentations. All tools are integrated into systems we call as intelligent PACS. To make it more useful, you should be able to handle all different kinds of lesions across the whole body. And therefore, it is also very challenging. So in this talk, I will introduce several works on the third part, the auto measurements. So when reading CT scans, an important step for radiologists is to measure the size of the found lesions. So accurately measuring the lesions is crucial in precisely precising the lesion growth rates across different time points. As such, it plays important roles in monitoring disease progress and making treatment plan. Currently, the most widely used clinic guideline of the lesion measurements is bi-dimension RECIST emitters. It consists of the implying longest axis and the orthogonal short axis. The manually labeling the RECIST emitters requires lots of professional knowledge. It is tedious, time-consuming, and prone to be inconsistent among the different observers. And these figures show the examples of where 3 radiologists manually annotated the RECIST diameters for the same lesions, as shown in the right image. Those 3 annotations indicated by different colors are different for birth and location. So one way to solve this problem is to develop models of some algorithms to automate this labeling procedure. So besides, some previous works have proved that lesion segmentation is a more powerful means to precisely assess multiple time points lesion or tumor change compared to the RECIST diameters. However, manually segmenting lesions are much more time-consuming and tedious than labeling RECIST diameters. That's why in the right now, doctor didn't manually segment lesions for their measurement. Therefore, so automatically and accurate segmenting the lesions are also very clinically important. So before introducing the proposed methods, I will briefly describe the main dataset and the evaluation criteria that we use. The depletion dataset is mainly used for training and testing of models. It is mined from the bookmark stored in NIH tags. It contains over 32,000 bookmark CT lesion instance with RECIST measurements from over 10,000 studies of about 4,500 patients. Well, these lesions covers over a variety of lesion types. For example, the lung nodules, liver tumors, also some larger lymph nodes, and so on. To evaluate the lesion segmentation performance, we manually annotated the piecewise lesions masks of about 1,000 lesions from randomly selected 500 patients. For the RECIST diameter predictions, the mean and standard deviation of the differences between the diameters length of the predictions and the ground truths are used for performance evaluations. And for some lesion segmentations, the DAS scores is used for the performance evaluation. Our first work about the automating the RECIST diameter labeling is done in 2018. We've developed those same models that contains 2 stages. At the first stage, we employed a special transformer network to normalize the lesion regions, which is obtained by a drawn bound box. So in the we hope in the normalized regions, the lesion is located at the center of the image, and its long axis is almost horizontal. Therefore, based on these regions, it's much easier to get accurate RECIST estimation results. At the second stage, we used a stacked hourglass network for a RECIST estimation, where we try to convert the RECIST diameter prediction task into a heat map prediction task. And that means if we can accurately predict the location of the 4 endpoints of the RECIST diameters, we will get accurate RECIST diameter predictions. This method requires radiologists or the users to draw one box that's covers the entire lesion. So this shows the results of the proposed method. The mean diameter errors on the depletion test set 1.89 millimeters and 1.61 millimeters for the long and short axis respectively. This figure shows 3 visual examples of the result produced by these methods. The first column shows the cropped lesion regions based on the bound box drawn by the radiologist. The second column shows the normalized lesion regions used by the first model. We can see that the lesions are at the center of the image, and their long axes are almost horizontal. And so from the 3rd to 6th columns show the predicted heat maps of the 4 endpoints. The locations of their maximums are considered the locations of the endpoints. The last two columns show the predicted RECIST diameters and the manual annotations respectively. So from these results, we can see that the auto RECIST results are close to the manual annotations. And we also can see from the last columns, for each lesion, there are 3 different annotations by 3 different radiologists. So like we can see that they are very different for both the locations and the size sometimes. So as we know, it's in the next work, I want to do something about the box-based lesion segmentations. So as we know, it's impossible to get a large number of fully annotated data to train lesion segmentation models. Or instead of using fully annotated data, we can try to use large-scale clinical RECIST diameter annotations to learn a powerful lesion segmentation tool or model. That means we have to train the model using the RECIST annotation. We can see from the right image, the left image, the white cursors, and the model can get the red covers as the segmentation results. And to solve these problems, we proposed a weakly supervised lesion segmentation models. So given a large number of RECIST diameter annotations, we first use some unsupervised image segmentation approaches to get a high quality lesion pseudomasks that are considered as the supervision to train the CM models. Here, the graph card algorithm is used for the unsupervised image segmentation. After that, we can get a pseudomask as supervision to train the model. After training the models using RECIST slices, we can inference the models on their label slices and get their lesion pseudomasks that are also added into the training data pool. So we then retrain the models, same models using more training data. So after iteratively performing the above processings until the model converge, we can get the final lesion segmentation models. So we can then using run or inference the final models on all lesion slices and stack their 2D segmentation result to get the final 3D lesion segmentation results. On the 2D and the 3D depth scores of the proposed method on the depletion test set, 90.6% and 76%, 0.4% respectively. So we can see that the 2D lesion segmentation result is promising, but the 3D segmentation performance is not that good. This figure shows 4 visual examples of the result produced by the proposed method. It can be seen that most of the lesion regions can be accurately segmented, but the method cannot segment the regions nearby the lesion boundaries, indicated by the yellow and the blue areas. Sometimes some region will be under-segmented or over-segmented. So to further solve these problems, we proposed a lot of weakly supervised lesion segmentation methods. So the title of this work is weakly supervised universal lesion segmentation with regional level set loss. There are 3 main contributions of this work. So the first one is effective network architectures. Tension enhanced high resolution network HRLite is built based on the HRLite by being augmented with a decoder and a lower tension mechanism, combining both dual tension and scale tension. The second one is a regional level set loss as a reformulated deep learning-based level set loss with specific modification is proposed for lesion segmentation. The third, HRLite and the proposed regional level set loss are integrated with simple yet effective weakly supervised training strategies, so that our models can be trained on large-scale packed story lesion dataset, for example, the depletion. This figure shows the framework of the proposed HRLite. And the regional level set loss is able to optimize the models reliably and effectively, so forcing the segmentation close to the lesion boundary. This slide gives the definition of the proposed regional level set loss. The first equation is the energy function of the classical level set methods used for image segmentations, treating the segmentation as an energy minimization problem. It contains 4 terms. The first two are the regularization terms used to measure the object size. They are sensitive to the object size. The last 2 terms are used to measure the intensity and consistency in the regions inside and outside of the objects, respectively. So we can make some specific modifications to get our region level set loss for lesion segmentations by first removing the first 2 terms, since the lesion size are highly diverse, and then we compute the last 2 terms from our constrained regions instead of the entire image region. The second equation is the proposed region level set loss, where the PAII is the predicted probability map of the PICCAI. And this figure shows 2 examples where the region inside the red cover is the constrained regions. As we can see, for the same lesions, the size of the constrained region remains stable under different data augmentation during training, for example, the random cropping or rotation. The 2D and 3D depth scores of the proposed method on the depletion test set are 2.6% and 86.6% respectively. It can be seen that the lesion segmentation performance is much better than the previous methods, especially for the 3D lesion segmentation. And this figure shows several rich examples of the results produced by the proposed method. The green and red covers represent the manual annotations and automatic segmentation results, respectively. And the yellow digits indicate the depth scores. The first row is the input CT image, and second row is the result produced by the proposed model actually trained using the proposed regional level set loss. And the third row is the result produced by the proposed model without using the regional level set loss. So from those results, it can be seen that when using regional level set loss, the results are much closer to the manual annotations than the ones without using the regional level set loss, meaning that through the optimizing the regional level set loss, the model can push or pull the segmentation results to improve the alignment with the lesion boundary. So I have introduced 3 box-based methods for RECIST and prediction and lesion segmentations. We can see from these 3 previous methods the performance of single task and the request users to draw a box that could cover the lesion regions, but it should not be too tight or too large. So such human guidance information is not user-friendly and increases the time cost. So to overcome these problems, 3 unified framework are proposed for automatic and simultaneous lesion segmentation and RECIST damage prediction over whole human body with just a single click gather informations. So those methods only requires a single click within the lesion regions, which is more convenient and efficient, without the need to carefully control the box size when drawing. And this figure shows the overview of the one-click guided lesion segmentation and RECIST damage prediction. So given a CT image, the radiologist only needed to click one near or inside the lesion. The rest will be done by the proposed methods automatically and accurately. So even different click points are provided, the methods can still produce similar results of the lesion segmentation and RECIST diameter prediction. So in these figures, the different colors means different click points, and their corresponding results, including the RECIST diameters and the lesion segmentation. That's the first unified framework. This figure shows the view of the first methods, which consists of two main components. One is the MRCN for initial lesion segmentation and the RECIST estimation, and the other one is the ARULET for lesion segmentation and the RECIST estimation refinement. As we can see that a given CT image and the click points, we can get accurate lesion segmentation and the RECIST estimation result automatically. The first component, MRCN, is used for simultaneously lesion of interest instruction, initial lesion segmentation and the RECIST estimation. So one click guidance provided by the radiologist is required as the input of the MRCN to effectively inject the one-click guide information into the models. A click image IC and a distant transform image ID are generated from the click points. Therefore, so we can construct a three-channel image as the input by simply concatenating the original 2D CT scan, CT slice, I and IC and ID. So as shown in the left image, extending the MICCAI, the proposed MRCN outputs or RECIST estimation results in parallel by adding a new branch for predicting the heat maps of the 4 key points, which are the 4 endpoints of the RECIST diameters. So the initial and the RECIST prediction obtained by the first components is not sufficiently accurate and fine-grained. So to improve this, we propose ARULET with a ULET-like architecture using RESTAT in the encoder and the decoder and the SPP as a junction between them for lesion segmentation and the RECIST estimation refinement. The 2D test scores of this proposed methods, the dependence test set is 91.2%, and the mean diameter errors are 1.75 millimeter and 1.56 millimeters for long and short axis respectively. This figure shows several visual examples of the results produced by this proposed method, where the automatic lesion segmentation results are very close to the manual segmentations, and the estimated RECIST diameters can will provide the information of the RECIST long and short diameters, of the lesions long and short diameters. So sometimes although the manual annotation cannot well touch the boundary of the lesion regions, our estimate results can fix them. You can see example indicated by the yellow dashed box. And from the previous methods, we can see that first, it extracts the lesion of interest regions by detection. Sometimes the detection results do not cover the lesions that we clicked in, because in some cases there's multiple lesions which are close to each other. So if we give a click on one lesion, the detection that will be given on another lesion. So second, the click information is introduced using the same construction strategy for different lesions. we're using the same parameter setting to generate the distant transform image for all lesions, the previous methods. So this strategy treats the lesions with diverse sizes and the shapes in the same way. So it may not be optimal to locating the lesion regions precisely. So therefore, to solve those problems, a new method is proposed to extract the lesion of interest region by segmentations rather than detection, and it builds a novel prior encoder to encode the click prior information into attention maps, which can deal with considerable size and the shape variations of the lesions. So we can consider it as a lesion-specific attention generation step. It also designed a scale-wide attention block with dual path connection to improve the decoders. On this figure shows the framework of the proposed method. Methods on the test set, different test set is about 92.4%, and the mean diameter errors are 1.73 millimeter and 1.52 millimeter for long and short axis respectively. This figure shows two examples of the result produced by these methods. And as we can see, give a CT image, the first column, and the click points, the red dot, the methods can first the method can segment the coast lesion regions, as shown in the third columns and the green curve. As you can see, green curve is not that accurate, but it can provide enough information to locate the lesion regions. So based on the coast lesion segmentation result, we can extract the lesion of interest regions, and as shown in the third, as shown in the second column. And then with this lesion of interest region as input, the models can further segment the lesion better and get better RECIST damage prediction results, as shown in the last two columns. Others, the previous two methods have been proposed for this task, but there is still some space to improve its accuracy and robustness. For example, enhancing the features by incorporating rich contextual information while keeping a high spatial resolutions and involving some new tasks and losses for joint optimizations. Therefore, to reach these goals, a transformer-based network is proposed for lesion segmentation and RECIST damage prediction. It is formulated as three correlative and complementary tasks, and in lesion segmentation, heat map prediction, and the key points regressions. To the best of our knowledge, it is the first time to use the key points regressions for RECIST damage predictions. So the proposed methods can enhance the high resolution features by employing transformers to capture on their long-range dependencies. Also, two consistent losses are introduced to explicitly build the relationships among those tasks for better optimizations. On this figure show the view of the proposed methods. So given a CT image and a click guidance, the red spots within a lesion, the top left and the bottom right corners, they're showing the green circles of a bound box. The bound box is showing the green dots box are predicted to indicate the lesion regions at the first step. Then a lesion of interest, the regions in the magnet box is extracted. whose center is the predicted box and whose width is the 2 times the extent of the predicted box non-side. So as such, sufficient context information is preserved in the lesion of interest. Then the lesion of interest is cropped and resized to 256 by 256. So at the second step, the results of the lesion segmentation and RECIST prediction are obtained based on the resized lesion of interest. The proposed network, the proposed transform-based network is used at both steps, and the detailed structure of the transform-based network is given on the right side. On the 2D scores of the proposed method on the depletion test set is then 2.7%, and the mean diameter errors are 1.56 millimeter and 1.37 millimeter for long and short axis. And this figure displays several quantitative results produced by our methods. We observe that first, the lesions are well located at the center of the extractor lesion of interest, meaning that the proposed network can accurately predict the corners of the lesion bounding box. Second, all automatic results are close to the manual annotations, and the diameter prediction produced by different tasks are nearly consistent, which visually demonstrates the effectiveness of our methods and the contribution of the proposed consistent analysis. In last rows, we can see there are 3 RECIST prediction results and manual annotations. All of them almost are very close to the manual annotations, and they are also very consistent. After that, we develop this tools, try to help doctors to do the lesion measurements. So further, we try to develop a deep learning system to automate the RECIST measurements in longitudinal CT studies using a simple click. And also we hope this a system can achieve comparable accuracy to the expert clinicians, but with markedly reducing time and labor efforts. So this deep learning system actually includes 2 or 3 key components. The first one is the key slice selection and the RECIST diameter prediction. The third one is the point matching or lesion trackings. So as shown in these figures, so give a CT scan collected at 10.1, then the radiologist just need to give 1 click and at the lesion, at any slice of the lesions. Then the system will automatically select the key slice where the lesion has the largest extent. Then second the lesion, and also do the RECIST diameter prediction. So as you can see, we can get the second. We can get the red slice and the RECIST prediction at the blue cross. So based on this information, we can use the point matching or lesion tracking tools to find or locate the lesions on a lot of CT scans collected at a lot of time. For example, 10.2, and then we can also use the same procedure to get the key slice and the lesion segmentation and RECIST diameter prediction results. So as you can see, for multiple time points CT scans, we just needed to give one single click at one time point. Then the whole system will automatically and accurately produce the RECIST measurements. So we test this system on 900 test lesion pairs. So it can achieve accuracy of 91%, and the F scores is also over 80% and then 90% for the tumor response classifications. And this figure shows 3 examples of the result produced by the systems. So the first column is it shows the clicked slice where you just give one click on the lesions, then the models will automatically select the key slice as shown in the second column. Then also segment the lesion and do the RECIST measurement. Here we just show the RECIST diameter prediction results on the third columns. Then using the tracking models, we can get the located lesions on the CT scans corrected at the 10.2. Also, we can get their key slice and their RECIST diameter prediction results. And the last column shows the response RECIST, shows the response results. As you can see, all response results is very has similar results as the manual RECIST annotations. Then I will show 3 demos to verify some applications that our system or methods can be used for. The first demo is to try to show the lesion segmentation results, one click-based lesion segmentation and the RECIST diameter prediction. As you can see, with the users or radiologists just need to give one click on either lesion regions. We can automatically and quickly get the results of the RECIST diameter and lesion segmentation. And you can give different key points on the simulation. The method will give the same or similar results. The worker also can see the method is trained on the lesion regions, but it can still work on some objects, for example, for liver, kidney, and as the speed is very quick, and sometimes if we just give one click, maybe the result is not that perfect. We can correct it by just draw a bound box. Yeah, this is a universal lesion tool, so it can work on different kinds of lesions across the whole body. So the second demo is try to demonstrate that how radiologists using our system to automatically annotate the 3D lesion segmentation mask. They give example of the lymph nodes. So the radiologist only needed to click once within the lymph nodes in any slice, and our system is able to automatically segment the lymph nodes in common slice. And then you can see the yellow regions on the left side. And then the center point of the segmentation mask is considered as the click points of a nearby slice. Based on this information, so our system can also segment the lymph nodes in the nearby slice. So after iteratively deal with all slices of the lymph nodes, we can stock their 2D segmentation results to obtain the final 3D segmentation results. So this video shows the demo that's how radiologists using our system to automatically do the RECIST measurements in longitudinal CT image studies. So with a simple click, so radiologists only need to click once within a lesion. Here, they also the same lymph nodes. Then in CT scans, then the system can find the lesion by lesion track on another CT scans, then do the 3D lesion segmentations. Then based on the 3D segment results, we can find the key slides, and then using the RECIST damage prediction models to get the final RECIST damage prediction results. Here, the red image shows the RECIST damage results with the, we can see the colored curves. So let's guess the conclusion parts. So as we can see, those methods I just introduced try to solve for clinically important problems. We hope to automatically and accurately measure the tumor size with minimum of just one click information, and hope the model can achieve comparable accuracies to the experts. Also, with the remarkably reduced time cost and the labor efforts. So this is a very, very important clinical program. And the third part is the second part is we can see that we try to use different strategies to improve the performance. For example, using multitask learning, introducing or better using the prior informations. Also using transformer to capture the long range dependence of the high resolution features. And third part is that actually we have deployed our system into some hospitals and the PACS components. And the doctors and the doctors have given us very positive feedbacks. Our system can get consistent results and accurate results, also can save a lot of time for them. On this slide shows the reference that's introduced in this talk. And that's the end of the talk. Thanks. So any questions?
Thank you, Youbao. That's a very wonderful talk, and the demo is super impressive. So if anyone has a question, there's a Q&A icon in the Zoom, and you can type your question there. Could I ask one question about the longitudinal study?
Okay.
So in the workflow figure, you showed how you should a workflow of time 1 and time 2. I was wondering, what if there are several images of it, how to handle this relationship between time to time?
You mean have many CT scans capture many time points?
Yes.
Yes. So for example, we have many CT scans captured from 10.1 to 10.2, 10.9, and 10.9. Then we can try to use our system to perform the procedure by every 2 times. For example, we can get the results, give a click at the 10.1, and then we can use our system to get the automatic results on 10.2. Then we can load the location of the lesions, all right? So we can use this information to get also click information automatically. So we can do the same procedure to on the next sample. So just do this intuitively to deal with all CT scans.
Yeah, that's a reasonable solution. Would the error be propagating? So if you made a mistake in the middle and the error just propagates to the rest, all the rest of it?
We didn't test using too many times. We just tested main pairs of just with 2 times. So then maybe there's some mistakes. If there's some mistakes, I think they need doctor to involve in the procedure.
Thank you. So there's a question in the Q&A box. So Masume, if I pronounce your name correctly, he or she asked that in addition to CT, have you used other modalities such as MRI to evaluate the model performance?
Yeah, that's a good question. Actually, we as we introduced in this talk, all models are trained on CT scans. Actually, we try to deploy or use the models trained on CT scans on the MR, for example, on the brain MR scans. We can also get some promising result. It's not that's good, but it's still very promising. If we want to make the models work very well on the MR scans, we have to train on all modules or this whole system on the MR images, I think.
Thank you. Any more questions? So if you have any question, you can also raise your hands and I will unmute you. It seems that there's no more question today. Oh, so a follow-up question. What are the missing points to fully deploy the deep learning models in clinical practices?
What are the missing points? What do I mean with the missing points? You mean the mistake?
It seems to me that is the gap between deploying it and the research work. Or I can unmute.
Yeah, if we deploy the system in clinical practice, that they have some mistake or missing points. Or gap between the research and the clinical use. So that's a real problem. So because we train our models on one data set, but we deploy on a lot of data domains. So maybe collected by different institutions. So there's a domain gap in them. So the performance also should have some gaps. How to deal with this problem? One solution is we try to fine-tune the models on that data to improve the performance. Yeah, we have to fine-tune. You have to collect some data and annotate some data, then fine-tune the models to make the gap be smaller.
Yeah, thank you. I have a follow-up question. So what kind of the data is used in your data set? Are they like CT images from the same institution?
Yeah, from the same institution, just on the edge. But I think the data is large scale, so they're collected by different devices, I think. But it is from the same institution.
Yeah, and for CT, the intensity is stable, but the noise level could be different. The slice thickness could be different.
Yeah, the slice thickness will be different.
So it's also different in your data set.
Yeah.
Great, thank you.
There's some.
Oh, there are more questions. Hi, Youbao. Thank you for the very interesting talk and overview of research. I was wondering whether you think it is worth pursuing a higher segmentation performance, Or do you consider this task solved now? That the resistant measurement error is below the inter-observer errors of radiologists?
Yeah, I mean, that's good questions. We did some experiments and tried to verify the inter-observation between the different radiologists or different or methods with different click points. And as in the demos, our model you can input different clicks. Our model can produce the same results. So we try to compute the standard deviation of the errors. For example, we try to click 10 times and we can get 10 different prediction results. So there is some standard deviation. We can compute standard deviation, right? So we can also ask many or two. In my experience, I just ask 3 results to do the same. Since to do the same thing, to measure the same lesions, we will get 3 different manual annotations. So we can also compute the standard deviation. So through our experiments, we can obtain that the standard deviation, the mean standard deviation of out results are much smaller than the human annotations. So that means the automatic results, the errors is below the radiologists, inter-observers.
That's great. Thank you, Youbao. Another question, is this tool available for downloading anywhere? Also, have you tested this on public available data set to validate on external data? For example, the cancer imaging archive.
Yeah, the tools Velo is not public because some company policy. So we cannot release the tools. And actually in our experiments in this talk, I didn't show the variation results on the external data sets, but in our papers, we did some experiments on the external data sets to verify the effectiveness of our methods. If you are interested, maybe you can get more detail about this external data variations on the paper.
Yeah, thank you. Do we have more questions? We are about the time. And thank you for this wonderful question, and thank you for your boss talk. The recording video of today's talk, if Youbao permitted, the video will be on YouTube. And thank you everyone for joining this talk.
Thanks, Sam.
Thank you.
Bye.
Bye.